to welcome in our second lecture. Complex analysis. We continue the previous theorem. We have seen up to equation 1. We continue the theorem. Hence, in the series summation an z to the power n from n to infinity, capital N to infinity, is dominated by the series is dominated by the series summation mod z divided by r to the power n. This is the right hand side series of the equation 1. Therefore, the series in the left hand side converges absolutely. This power series converges absolutely. Converges absolutely for each z, for each mod of z less than r. Since mod of z divided by r is less than r, this ratio is less than r. Therefore, the power series on the LHS of equation 1 converges. Implies the power series on the LHS of equation 1, that is left hand side series summation an z to the power n from n to infinity converges absolutely. Converges absolutely. This is because the right hand side series of the equation 1 is converges. Hence, the left hand side series summation an z to the power n is converges absolutely. Which proves the part A. Which proves part A of the theorem. Then we go part C. Then we prove part C of the theorem. Let r is less than r and we choose row such that row lies between r and r. This row lies between capital R and small r. Therefore, as in previous part A, let n be such that, let capital N be such that mod of an is less than 1 upon rho to the power n for all n greater than equal to capital N. Therefore, if mod of z less than equal to r, then we have mod of an z to the power n is less than equal to r upon rho whole to the power n, and this ratio r by rho is less than 1, which is the equation number 2. Then we use the Weierstrass M test. Therefore, according to Weierstrass M test, by Weierstrass M test, the power series given by summation a n z to the power n from 0 to infinity converges uniformly on the set z such that mod of z less than or equal to r, which implies the part C. That is, we prove the part C. Then to prove part B. To prove the part B, let mod of z greater than r and let r with mod of z greater than r. This is as in we have seen in the part B, which implies taking the reciprocal we have 1 by r, the greater inequality becomes less than 1 upon r. Then we use the definition of limit supremum. By definition of limit supremum, this gives infinitely many integers n. This gives infinitely many integers n. Many integers n with 1 by r less than mod a n to the power 1 by n. Therefore, we multiply by mod z on both sides of the equation. Therefore, mod of z by r less than mod a n to the power 1 by n into mod z. We multiply this equation by mod z on both sides. Therefore, we take the power n on the left hand side. Therefore, mod of z divided by r to the power n less than mod of n to the power 1 by n to the power n cancels, so we have mod n. We can take combinedly the power of this as n. We have taken power n on both sides of the equation. Now this is less than this, therefore the right hand side is greater than the left hand side. Therefore we write mod of z right hand side, that is mod of a n z to the power n, which is greater than left hand side, that is mod of z divided by r to the power n. Now this, by this equality, this is greater than this, therefore we say that the series become unbounded. Therefore, the series becomes unbounded. Series become unbounded since mod of z by r greater than 1. Since mod of z by r is greater than 1. Now in this, the theorem is completely proved. Then we take the next theorem. It is in the form of proposition. Proposition. If summation an z minus a to the power n, that is this series, is given power series, is given power series with radius of convergence r, with a radius of convergence r, capital R, then r equal to limit mod of an divided by an plus 1 if this limit exists. If this limit exists. Let's see the proof of the theorem. Proof. Let a equal to 0. As in the previous theorem. And let alpha equal to limit of an divided by an plus 1. This is equation 1. And suppose this limit exists. Let this limit exist let r lie between mod z and r. Let r lies between mod of z and alpha, and find integer n and find integer n such that r is less than mod of n divided by n plus 1 for all n greater than equal to n, which is equation 2. Let b equal to mod of n r to the power n, then we have mod of n plus 1 into r to the power n plus 1 equal to, by property of indices we break this as r to the power n plus 1 as r to the power n into r. Therefore we have mod of n plus 1 r to the power n multiplied by r by property of indices, which is less than mod of an into r to the power n. This quantity is less than mod of n into r to the power n. Now in equation 3, this is nothing but b, therefore we write less than b seen by equation 3. Now consider this as equation 4. Now we are seeing this mod of n plus 1 r to the power n plus 1. Then we see expression for mod of n plus 2 r to the power n plus 2. Similar to this, take similarly mod of n plus 2 r to the power n plus 2. Again by property of indices we break this r to the power n plus 2 as r to the power n into r square. Therefore we can write it as mod of n plus 2 r to the power n into r to the power n plus 1. By property of indices we write here n plus 1 plus n, that is r into 1 minute. This r to the power 1, r to the power n plus 1, therefore we get addition, that is r to the power n plus 2. Now this is less than n plus 1 into r to the power n plus 1. This expression is less than n plus 1 r to the power n plus 1, which is less than b, seen by equation 4. Therefore we continue this. We have an plus 2, then we take an plus 3 r to the power n plus 3. Again we get less than b. We continue this process.